Okay, this lesson is for section 1.2, functions and graphs, and we're just going to start out with the definition of a function, which is a correspondence between a first set called the domain and a second set called the range, such that each member of the domain corresponds to exactly one member of the range. So everything in the domain can only go to one thing in the range. So let's look at example 1, and this is a mapping, and it says determine whether each of the following is a function. So this is our first one. We have -6 going to 36, 6 going to 36, -3 going to 9, 3 going to 9, 0 going to 0. This side on the left would be considered the domain, and this side on the right would be considered the range. So what you're trying to check is, does each thing in the domain only point to one thing? Well, the -6 only points to one thing, the 6 only points to the one thing. It doesn't matter that that's the same thing, it's just one arrow coming off of that number on the left. So none of these over here have two arrows coming off of them. Okay, over here, I mean, everything can be pointing to the same number and it would be fine. So this is a mapping and this is a function. So we're going to say, yes, this is a function. That helps us out. Let's go on down to our next example. And sometimes it's not numbers. Sometimes it's things that are not number related. Here we have a chart with some different presidents and a chart with Supreme Court justices and who appointed them. Okay, so that's the relationship. So George H.W. Bush appointed Clarence Thomas. George W. Bush appointed Judge Alito and Judge Roberts. Barack Obama appointed Judge Kagan and Judge Sotomayor. And then Bill Clinton appointed Judge Breyer and Judge Ginsburg. So the question is this a function? And so again, doesn't really matter what's happening on the right and how many arrows are pointing to what, although a judge can obviously only be appointed by one president at a time. It's what's happening over here on the left. And you can only have, again, one arrow coming from each thing in the domain. And George H.W. Bush, he's good. He's only got one arrow. But George W., Barack Obama, and Bill Clinton each have two coming from them. And that is what makes this not a function. So this one is not a function. Okay. This one is a little bit different, example 2. And in your book, it'll have a middle column probably that's telling you what's going on. But I just broke this down to domain and range. Okay, again, this is a little bit different because you're actually going to take each thing separately and think about what would be in this description. So the first one is the years in which a presidential election occurs. So those occur every 4 years, and we could make a list of those years. So if we think about that being a domain, and then the range is your set of presidents. Okay, so is it possible for a year that a presidential election occurs to have two arrows coming from it? Okay, in other words, it would point at two different presidents. And obviously that would be impossible because when an election occurs, we only have one president at a time. So each year that we're talking about here would point to one president in the range. And so, yes, this first one is a function. Okay, let's move to our second situation. It says all automobiles produced in 2016. And so if you think about, you could list all the Chevys, all the Fords, all the Toyotas that they came out with this year, and make a list of those. And then, but it would be, I think they're also talking about every single one. So, I mean, you know, there might be 300 or 1,000 of something produced. And then the set of VINs. Okay, and so a VIN is a vehicle identification number, and each vehicle has a different one. So if you think about it, if I listed every single possible automobile made, You know, let's just take for a second a Chevy Tahoe. I'm just randomly guessing. Let's say they made 1,000. You would have 1,000 Chevy Tahoes listed. Each one has a different VIN number, so each one would point to a VIN number that was unique. So, I mean, it's almost just a straight across picture in your head. And so, yes, this would be a function because each car would only have one VIN number. A car couldn't point to two VIN numbers, couldn't have two VIN numbers. All right, C, we have all the professional golfers who won a PGA tournament in 2014. So if we listed all the professional golfers who won, make a list of that, or imagine making a list of that in your head. I'm not very familiar with those. And then the set of all PGA tournaments in 2014. Okay, so would a golfer only point to one tournament? Okay, well, I'm not familiar with the golfers, but I think it's possible that you could have a golfer who won tournament over here that could have won more than one tournament. So they could have arrows pointing to 2 or 3 different tournaments. And so if that's possible, that makes it not a function. All right, and then we move down to D. And again, back to golf, we have all the PGA tournaments in 2014. So if we listed all the tournaments, and then the set of all golfers who won PGA tournaments, each tournament would have one winner. And so you would point one arrow from each item in this list to an item in this list. Now, you know, some of those might point to the same person, as I discussed, because it's kind of backwards from what we did in C. But the point is that in this left side, everything would only have one arrow coming from it if you were drawing a kind of mapping of it. And so if that's the case, then we have to put yes, this is a function. All right, a relation, you may have thought of it as the opposite of a function, but it's really not. They're related. A relation is a correspondence between domain and range. You have a domain and range with a relation, but each member of the domain corresponds to at least one member of the range. In other words, it can have more than one arrow coming from it. So a lot of things would fall into relations. The C that we just did would be a relation. So let's move on. And again, we're back to determining whether it's a function or not, and we're going to identify the domain and range. So when I'm looking at a set of points, I want the x values to be unique, okay? Because if you were to line up your x values here and your y values here, think about how many arrows would be coming from it. In this case, 9 would be pointing to -5 and 9 would be pointing to +5. And so you'd have 2 arrows coming from 9. And so this is not a function. But we can still identify the domain and the range, and I just kind of shorthand it with a D and an R. I'm going to use that curly bracket and just list the domain. And so the numbers in the domain, you have 9, 9, and 2. So I'm just going to say 9 and 2. I don't need to repeat that one. And then the range is your y values. And so I have -5, +5, and 4. And again, I'm going to use the curly bracket, -5, +5, and 4. Close that out. All right, let's examine B. Again, I want to look for unique x values. I have -2, 5, 0, and 4. So nothing is repeated. If I listed those out in a mapping, they would each only have one arrow coming from them. So this would be yes, it is a function. My domain again is the list of all the x values. So I have -2, 5, 0, and 4. My range is the set of all the y values. So I have 5, 7, 1, and -2. And then I have C, again looking for unique x values. So I have -5, 0, and 6. Nothing is repeated. If I were to do a mapping, it would be okay. So yes, this is a function. The domain is going to be my x's, which are -5, 0, and 6. My range will be my y values, 3, 3, and 3. And since it's all the same, I really just can put a 3 in the brackets and move on. Ooh, went too far. Sorry, excuse me. Okay, the next thing I need to talk about is function notation. And you've dealt with this before. It's just using f of x. You're probably using f of x equals y and thinking that those are interchangeable. But when you're using function notation, what you need to realize is that f parentheses, whatever's in the parentheses, is your input. This is your domain. And then whatever comes out of this, what is your output, that is your range. So domain is like input, range is like output, and you can always figure out what you're putting in by looking in those parentheses. And so number 4 is an example of that. I have a function in function notation, f of x equals 2x squared minus x plus 3. And they are asking me to find f of 0, and hopefully that's familiar looking to you. And basically that means plug 0 in. So I'm going to take my x's out and put 0 in. And obviously 0 squared is 0, 2 times 0 is 0, and this whole piece ends up to be 0, so that is 3. My output is 3. And so just in this case, I would be talking about a specific point where the input was 0, the output was 3. 0 would be a member of the domain, and 3 would be a member of the range. Alright, let's move down just a bit. Same function, but we're going to plug in negative 7. And so I'm going to do 2 times negative 7 squared minus negative 7 plus 3. And when you're doing things like this, remember the order of operations, the PEMDAS, please excuse my dear Aunt Sally. You need to do this parentheses and exponents first. If you're typing in, make sure you put that negative in the parentheses with the 7. If you're doing it in your head, you're thinking negative 7 times negative 7, which will give you a positive 49. And here you have a negative minus a negative, which will become plus a positive. So if you calculate all that, you should get 108. And if you're just needing to practice typing in your calculator, go ahead and type it in and make sure you get 108. Now, you're also going to get some weird looking things. This one has a variable with it. We have 5a that we're plugging in. You still do it like you did the 0 and the negative 7 though. You want to take the x's out, put 5a in. So I have something that looks kind of like this. And what ends up happening is you end up combining like terms. You're going to have to do a little bit of work, and then you're going to combine like terms. So again, I want to start with that parentheses and exponent, which comes before multiplication. So I need to just hold on to the 2 because I'm going to have to multiply it after that. This 2 squares the 5 and the a, so I get 25a squared. Then again, I'm going to think of that as minus 5a plus 3. And then I can multiply. 2 times 25 is going to give me 50a squared. And then I have minus 5a plus 3. And I can't combine any of those because the a's have the different exponents. So as strange as that looks, where the other numbers were outputs that were numbers, this output is like a polynomial look. And that's okay. Now, D is similar, but you've got to do a little bit more work. So again, I'm just looking inside the parentheses. It tells me I'm going to plug in a minus 4. So I take my x's out. I put in a minus 4. Make sure at this part you put it in parentheses because you'll need to distribute that negative. And then, if you'll remember, it's probably best to write this one twice, a minus 4, a minus 4, because you can't just say a squared and 4 squared like you could up here. This minus makes it have to makes you have to do FOIL or double distribution, however you want to call it. I'm going to have to do another step to that part, but I'm going to come over here and go ahead and distribute this negative in and get a negative a and a positive 4. Then I'm going to come down. This one takes a little bit more work. I'm going to FOIL. So I have a times a is a squared. A times negative 4 is negative 4a. Negative 4 times a is negative 4a. Negative 4 times negative 4 is a positive 16. And then I have the minus a, and I'm going to go ahead and say that's plus 7. Then I'm going to distribute the 2 through. get 2a squared minus 8a minus 8a. So I'm going to combine those. Get minus 16a. And then plus 2 times 16 will be 32. Bring these down. And then finally, I have 2a squared. I have a negative 16a and a negative a, so that'll be a negative 17a. And then 32 and 7 will be 39. And again, I have a pretty large answer that has a polynomial look to it. Okay, moving on. We need to be able to graph, and you need to be able to graph a couple of different ways. I'm going to take this A part of number 5 and show you how you can always graph even if you don't have a calculator. So if you have a standardized test and you need to take it without a calculator, you can do this. Or if you forget your calculator on test day, you'll have this, hopefully, be able to use it. So I'm going to make a table of values, x and f of x, and I can pick any x values that I want, and I like to pick ones that are small enough to work with in my head. So I'm going to say negative 3, negative 2, negative 1, 0, 1, 2, and 3. Just because those are easy to work with, and it gives me some negatives, some positives, and it's always good to plug 0 in and see what happens there. So what we're going to do is plug those in, kind of like what we were doing in example 4 with the numbers, but I'm going to do it in my head. If you need to write it out, then write it out. So I'm going to do this in my head and discuss it as I go. So I have negative 3, I'm going to square that and get 9, and then subtract 5, so I get 4. If I plug in negative 2 squared is 4, minus 5 is negative 1. Negative 1 squared is positive 1, minus 5 is negative 4. 0 squared is 0, minus 5 is negative 5. 1 squared is 1, minus 5 is negative 4. 2 squared is 4, minus 5 is negative 1. 3 squared is 9, minus 5 is 4. And as you can see, it's going to make a parabola, which hopefully you knew. So let me take a minute to get us ready to graph. Okay, so now I have a grid. I'm going to go ahead and get ready to graph. And so I'm going to treat these like points. I have the point negative 3, 4. So I go back 3 and up 4. Put a point. Then I have the point negative 2, negative 1. So negative 2 would be left 2 and down 1. And then negative 1, negative 4, so left 1, down 4. 0, negative 5, so straight down 5. Then I have 1, negative 4, 2, negative 1, and 3, 4, and makes a nice parabola that you can connect. And you know, parabolas go on forever. We just chose these x values, but we could have chosen any, and it does go on forever. Okay, now let's talk, how would you graph something in your calculator? Because you can always make this table of values, and you may need to do that in some of the problems that the book gives you. But let's talk calculator here. So in your TI, if you hit the window button, your standard window is negative 10 to 10 on your x-axis and negative 10 to 10 on your y-axis, and that's going to come up in some of those questions about the standard window. It should be preset to that, but if you've been changing it or working with it, it might be off and you might have to redo it. You want to go, after you've checked your window, to the y equals button, and that's where you can type this in, and you'll just be typing this part in. And you can get to that power to put the 3 in with the little upside down V looking key that's just above your division button. But when you type it in, it should look like this. And then if your window is standard, you graph it and you'll get the shape. And so what I'm going to do is stop for a second, let you graph, go ahead and hit pause, and then we'll see what that looks like. Okay, so when I graphed mine in a standard window, it looks something like this. It's the best I can sketch it, but it's your basic cubic shape. Now, if you needed to know exact points, like we had this table up here, you can hit the table button on the calculator and it will show you some of the exact points on there. If you need assistance with this, please raise your hand and call me over. Okay, for C, I have a square root function, and so you can find the square root above the little x squared button, so you'll have to use the blue second button to get it when you're graphing. But again, if you go in a standard window, it's going to look something like this. And if you have your scales marked, your x scales marked at 1, you'll be able to see that this is actually at 4. It's moved forward to the left. Some of you might remember your shifts of functions. But again, if you need the exact points, you can always look at the table and it will give you those x's and y's if you need them. Okay, for example 6, we have a function and we want to use the graph to find the values. So what I want you to do is go to y equals and plug in x squared minus 6 and graph that. And you should see a parabola that's been moved down 6. And to figure out what exactly f of -3 is, hit second trace, which is calc in blue, and that first option is value. If you hit that, it'll say x equals. And so since x is our domain and -3 is our input, which is our domain, I'm going to type -3. And it will give me the y value, and so that's what I'm looking for. And in this case, it's a +3. You can always check by plugging it in, like we did in the previous example. We're just plugging -3 squared and then -6, and you know it's 3. But just to practice with your calculator, again, let's do the f of 1. So now that it gave you the answer to -3, you'll have to do second trace again and select value again and type in the 1. And in this time it gives you -5. If you need help with this, please raise your hand and I will help you. Alright, next we're coming up on the vertical line test, which is something that you're probably familiar with. It says if it is possible for a vertical line to cross a graph more than once, then the graph is not the function, the graph of a function. So if a vertical line passes a point more than once, on that graph, then it's not a function. Okay, so now I've added some graphs in. We'll just look at them and decide if they're a function or not. So again, think about a vertical line. If you can put a vertical line anywhere on that graph and it only touched one point, then it's good. So this first one is a good example of a function. So yes, this is a function. This next example, I can put a vertical line right here and touch 3 places with that line. 3 places on that graph with that line. So that is clearly not a function. Over here I have something that's kind of like a C shape. And again, if I could draw straight, but if I put a vertical line there, I can still touch 2 points on that graph at the same time. And so that's not good. It's not a function. A circle is the same way. I can draw a line here, I can draw a line here, and I'm touching 2 points at once. This next graph is kind of pointy and sharp, but anywhere that I draw a vertical line, I'm only touching 1 point at a time, so we're good. This last one is a piecewise function. Some of you may have seen those, some of you may not have seen those. And the question becomes, it doesn't overlap anywhere except like right here. Everywhere else, if I drew a vertical line, it would only touch in one place. But the question is right here, this line through these points. And you have to remember that if it's an open circle, that point isn't actually there. If it's a closed circle, it is. So technically, this vertical line is only touching this point when it's passing through here. You just have to remember that open circle means it's not actually a point. And so, summing up this line, we have not a function, yes, this is a function, and yes, this is a function. Okay, then we're going to move on. And it says find the indicated values, function values, if possible, so it may not be possible, and determine whether these values are in the domain of the function. Here I've written a fraction. It's kind of hard to type, so this is the same thing as 1 over x minus 3. That's what I was meaning right there. And so we are looking at f of x equals 1 over x minus 3. And we want to find f of 1 and f of 3 and determine if those are in the domain. So let's plug in 1. If I do f of 1, I have 1 over 1 minus 3, and so that will give me 1 minus 3 is a negative 2, so I get a negative 1/2. And so that would mean that there's a point on that graph that is at 1, negative 1/2. And so yeah, that's good. 1 would be in the domain because it does have an output in that function. 3, f of 3, if I plug that in, I have 1 over 3 minus 3. Well, 3 minus 3 is 0. And 0 can't be in the denominator. 0 on the bottom of a fraction is not good. It actually means it's undefined. And so there is no point. 3 is not in the domain of the function. There is no point with an x value of 3. What's actually happening, some of you may remember, is that there's a vertical asymptote here, and we may get into that later, but not today. So just know that for today, it's not in the function. It's not in the domain of the function. All right, on this next one, we have g of 16 and g of negative 7. And I'm going to make one correction here. This is supposed to go just over the x. So that's what we're going to be looking at. I'm going to first look at g of 16. So I'm going to do the square root of 16 plus 5 to come up with that output. The square root of 16 you know is 4, so I'm looking at 4 plus 5, which is 9. And so since I got a 9 as an output and 16 was an input, that means that I have the point 16, 9 on that graph, and it looks like 16 would be part of the domain. Now if I look at negative 7, g of negative 7, it would be the square root of negative 7 and then plus 5. Well, when you're dealing with square roots of negatives, you're getting into i's, imaginary numbers, and we are not ready to deal with those yet. So we're going to say that negative 7 is not in the domain of this function. If you were to graph this, you would notice that there are no points with an x value of negative 7, because with an I, it's not going to show up on your Cartesian plane. All right. And number 9, we are looking at the domain of these functions. So I think it's best sometimes to figure out what's not there. And we looked at one just a minute ago where that 3 was giving us a 0 on the bottom of a fraction, and that wasn't in the domain. And so let's think about what that would be here. And what would I plug into this denominator? And again, remember, this is like saying 1 over x minus 7. I just had to type it out a little differently. What would we plug in that would give us a 0 on the bottom? Hopefully you would realize that it would be a positive 7. And anything else that you plug in, you're going to get a number, so it's going to work. That means that your domain for this would be all real numbers not equal to 7. Or you could write it negative infinity to 7 and 7 to infinity, or you could use the less than or equals to do that. So those are a couple options there. Okay, with b, we have, again, a fraction, and think of this as on the top and this is on the bottom. And if you'll remember what I was talking about up here, with a fraction you just can't have 0 in the denominator. You could have 0 in the numerator, and that would be okay. It just can't be in the denominator. So really, we don't even have to worry about the top of this fraction. You just have to worry about the bottom. So if you get a fraction, again, don't worry about the top. I'm just going to write it down, not even really thinking about it too much. But I'm going to factor the bottom because that's easier to look at. Just because this x minus 7 was simple, I can make this simple by factoring and see what I could plug in that would give me a 0. So what multiplies to give me 3 and subtracts to give me 2? Be 3 and 1, and I need it to be positive. So factoring that out, what could I plug in? Look at each one of those separately. Here, if I plugged in -3, I would get a 0. Here, if I plugged in 1, I would get a 0. So my domain is going to be all real numbers not equal to -3 or +1. And there's other ways that you could write that, whatever works for you. Okay, let's move to C. Well, x cubed, hopefully you know that any number that you plug in, you can cube it and get something out, so you're good. Absolute value of x, any number that you plug in, you're going to get something out because it just turns it positive. Even if I plug in a negative number, so if I plugged in -3, I would get a +3. So there's really no problems like there are here because, you know, fractions can't have 0 on the bottom, but these work. There's no issues. And so the domain of this is all real numbers. Okay, and then finally for D, we're looking at the cube root of x minus 1. Okay, I want you to think about this. Is there any number that you could plug into the cube root of x minus 1 that would give you something you're not allowed to have? Okay, so somebody's first instinct might be, hey, what if I plugged in 1? Because that would give me a 0. Well, the cube root of 0 is 0, so you're still getting an answer out. What if I plugged in like -1? Okay, that would be the cube root of -2, which is a decimal, and I'll have to even figure out what that is, but it's still a number. Okay, so cube root of -2, I'm just typing it in, is -1.25. You're getting an output, and the reason you're getting an output is because unlike a square root, you can take the cube root of a number that's negative. So a cube root can be taken of negatives and positives and still give you outputs. You can also look at the graph, which is what we're going to do in number 10, to kind of verify to yourself that this domain is all real numbers again. Okay. Now, like I said, number 10 is asking us to use the graph. And again, that's what I would check D with because that would just give me some peace of mind, especially if I wasn't as comfortable with roots. And so what I would like for you to do with number 10 is take a minute and graph each of these in your calculator and see what you think the domain and range are. Okay, so let's check these. Your first one is a line with a slope of 1/2 and a y-intercept of 1, and so a line would be going kind of diagonal in the positive direction, and it doesn't have any problems with it. So the domain would be all real numbers, and the range would be all real numbers. Okay, and moving on to B, your square root of x plus 4, that's one we looked at. It's that square root graph that's been moved left 4, and so that would make your domain all real numbers greater than or equal to -4, and your range all real numbers greater than or equal to 0. And if you're having questions about how I got these, please raise your hand and call me over. And then x cubed minus x is a graph, again, we looked at previously in the notes. So I know that the domain is all real numbers. There were no issues with it. And the range is also all real numbers. So again, if you don't understand any of those, call me over. Okay, D goes to another fraction. So remember, you can't have 0 on the bottom. So we think about what would make 0 on the bottom, and that would be a +2. So your domain would be all real numbers not equal to 2. And if you look at the graph on your calculator, it does go down forever and up forever, but it jumps over 0, and so your range is going to include everything but 0. So range is all real numbers not equal to 0. E is x to the 4th powered polynomial, and polynomials are continuous and keep going. And so we're going to look at our domain as being all real numbers. And this graph kind of makes a W shape, and so if you're on your calculator, if you look, the lowest it goes is -4, and you can explore that by using the table or the trace or plugging in that value function, and it will actually show you that lowest it goes is 4, or excuse me, -4. So your range has to be everything greater than or equal to -4. All right. And then for our last one, domain and range. This is one I'm not sure of the shape. Some of the others I just kind of have the shape memorized. But this one I had to plug in, and it almost looks like a semicircle. And it may very well be because, you know, our window of our calculator is wider than it is tall, so things are a little distorted. So looking at this, it looks like on my calculator the domain starts at 1 and ends at 5. So it also includes those numbers. I'm going to put this square bracket, which means it includes that number. And so 1 to 5 would be our domain, and that is called interval notation. You may also write it like this. That may be more familiar to you. The range, it looks like it goes from 0 up to 2. So again, I'm going to use this interval notation. I'm including the 0 and 2 because it looks like there's actually values that have those y's. I can write it like this in interval notation, or I can write it in the standard notation that you may have learned. And again, notice I'm using X for domain and Y for range. This finally concludes our notes, and feel free to ask me any questions that you need a little bit more information about.